Hi there, Mr. Sutton here with the AB Calculus 615 homework solutions on integration with respect to y. For this problem, they want us to find the area of the enclosed region here. Now, the first thing I notice is these functions are in terms of y, plus we have this horizontal line at y equals 0. So I'm going to go ahead and graph the line, and then I'll use my draw inverse capability on my calculator to draw these other functions. So here's what I've got in my y equals so far. I actually put these two functions in my y equals as y1 and y2, but I used x instead of y because later on I'm just going to do draw inverse, and then I'm going to use y1 and y2 to plug into that to graph these things on the calculator. And I also put in y equals 1 for my horizontal line. Let me do zoom 6 just to get my horizontal line out there. And let's see, I actually could probably zoom in a little closer to that. Let me do zoom 4. There we go. And while I'm at it, I'm also going to do draw inverse now on these functions. So I'm going to do second and then program, so that's the draw menu here. Option 8 for draw inverse. And I'm going to draw the inverse of this first one. So I'm going to do, let's see, alpha trace y1. And that's going to give me y squared minus 1 when the calculator actually interprets this. So pressing enter, there's what that function looks like. It's this little sideways parabola. Let me do this other one now. So I'll quit out and I'll do draw inverse of alpha trace y2. And here's what that looks like. So there's what I have in my calculator. We have this little region in here that we're trying to find the area of. Now this is going to be kind of a pain if you're trying to do it vertically with respect to x, because the bottom function changes once you get to this little intersection point here, which means you're going to have to find the intersection point, and then you're also going to have two different integrals. This is actually a lot faster to do with respect to y. For one thing, there's functions already expressed in terms of y. For another thing, we only have one right function and one left function, so that's just one integral we have to deal with. So I'm going to do, let's see, I need my limits of integration. So I'm going from bottom to top here. Where do these things intersect? So let me go ahead and actually figure this out on the calculator. Now there's two ways to do this. One way is to convert these to functions of x, graph them both out, and find the intersecting y value. That's the long way around. Another way is to just graph these with x instead of y, see the x value at which they intercept, and then that's actually going to be the y value on this graph. I'm going to use the second approach, so let me show you that. So at this point now, I don't really need this picture anymore, so let me just get out of here, and I'm going to do second draw, and I'm just going to clear my drawings out of there. And now let me go back to my y equals, and I'm actually going to enable my y1 and my y2. And I'm going to disable this horizontal line at this point. I don't really need to graph that anymore. Really, I'm just graphing these two things so I can figure out where they intersect. So let me do now second and second trace, and then intersect, option 5. So here's my sideways parabola graphed as a vertical parabola, and here's the sideways square root as a vertical square root. So let me just see where these intersect over here. This is the one intersection place. Enter, enter, enter. So the x value at which they intersect is this 1.4902 value, and I know that's really the y value right here on this graph where they're intersecting. So I'm going to go ahead and store that on my paper as p. I'm going to say y equals p approximately equals to this number. On my calculator, I'm also going to store that value. So I'll quit out of my graph, and I'm going to do store, and then alpha, whatever you want. I'm going to do alpha p, though, because that's what I wrote on my paper. Now I can use that whenever I want. So to find the area, then, I'm going to need to take the integral from 1, that's the bottom y value here, 1 to p of, now I have to do right function minus left function. The right function is the little square root thing here. That's the g function. And the left function is the f function here, this sideways parabola. So I've got g of y minus f of y dy, and it's back to the calculator for this. So to do this on the calculator, I'm just going to integrate everything and pretend everything is x's on the calculator. As long as you're consistent with the letter, you can get away with this. So I'm going to do math 9 integral from 1 to, let's see, alpha p. So there we go for my limits. And in here, I'm going to just do, let's see, alpha trace y2, because that's where I stored my g function, minus alpha trace y1. And again, these are both expressed in terms of x on the calculator, but I'm going to write dx here, so my calculator is going to treat it just like this integral down here is treating all the y values. So pressing enter, that gives us about 0.267, and we're going to go with that. For this problem, they want us to find the area enclosed by radical x plus 2 and x and the horizontal line y equals 3. So I'm going to take a moment to graph all these out. And I have a hunch these are going to be pretty close together. I'm just going to do a zoom 4. Oh, that's not enough. All right, let me do something a little bit further out. Let me do zoom 6. There we go. And you can, of course, zoom in on this area. You're basically looking at this if you were to zoom in a little bit more and adjust your window. So this is going to be kind of a pain to find the area of if we're going left to right, top minus bottom, because you'll notice here at this spot, it looks like x equals 3. We're switching bottom functions from 3 to this x function here. So if you want to do this in one integral, you're going to have to integrate with respect to y. And in order to do that, you're going to have to convert these into functions of y. So I'm going to go ahead and do it that way, just because this is a homework about integrating with respect to y. But you could do this with respect to x if you use two integrals. So converting this first one to y's, we've got, let's see here, subtract 2 from both sides, so that's y minus 2, and then square both sides to get x by itself. So we can write f of y equals y minus 2 quantity squared. And for this other one, well, this is actually pretty easy. Instead of writing y equals x, we can write x equals y. So f of y equals y for that one. And then we still have that horizontal line. So now, at this point, I'm going to use these functions to find the area. But before I can do that, I also need limits of integration. My bottom y value here is going to be 3, because that's a horizontal line that they gave me. How about the top function up here? It kind of looks like 4. Let's just do a quick check, though, by plugging in here. I mean, I could find it on the calculator, but plugging in is going to be pretty quick. So if I do the square root of 4 plus 2, that's 2 plus 2, which is 4. And if I plug in 4 here, well, I've still got 4. So I do get the same value when I plug in the same x value. And I also get back the y value of 4 for both of those. So definitely y equals 4 is where these are intersecting. So I can say these equal each other at y equals 4. If you wanted to be safe and check it on the calculator, you could always do a second trace and see the intersection of these things and just pick out the y value, which you will again find is 4. All right, so getting the area. I've got the integral from 3 to 4 of, now it's going to be right minus left because I'm doing this with respect to y. So I'm going to have, let's see, the right function is this line, g of y, and I'm going to subtract from that this other function here, which I'm now calling y minus 2 quantity squared, or just f of y. So g of y minus f of y, and dy out there, not dx. Now I'm going to need the calculator to actually do this. So I've got the integral from 3 to 4 of this stuff. I would love to just do an alpha trace and pull up my y1 and y2 menu and plug those in. Unfortunately, I've expressed my y1 and y2 in terms of x, not y. So you either need to put in different versions of y expressed in terms of y like we have here, y minus 2 squared and y, or you can just simply enter those in as x's directly into the integral. I'm going to do the second of those things. So instead of writing y minus 2 quantity squared, I'm going to write x minus, parentheses, x minus 2 quantity squared. And let's see here, I don't think I need any more parentheses, so let me just move straight over here to the dx and press enter. Gives us about 1.167. On this problem, I want to find the volume of the solid obtained by rotating this bounded region between this 3 minus y function and the y and the x-axis, rotating all of that about the line x equals 3. Let me start by putting this in my y equals and drawing inverse on this to get a function in terms of y drawn out. So I've entered this in my y equals as 3 minus x, because in a second I'm just going to do draw inverse on this thing, and it'll treat it like 3 minus y. So quitting out of there, I'm going to do second and then draw, second program to get my draw menu. Option 8, and I'll do draw inverse on alpha trace y1. And that gives us this line here. So I basically want the area between this line and the two axes. So this little triangle shape in here. And I want to revolve that around the line x equals 3. So that's a vertical line going through 3. So in order to do this, I'm going to need washers because I've got a space here between my bounded region and the axis of revolution. So I'll set up as my general archetype here, a of y equals pi times big R squared minus little r squared. And now I have to find out my two radii. So for big R, I've got the axis of revolution, the distance between this and the part of my bounded region that's further away. Well, the further away boundary is just the y-axis, which is just x equals 0. So my big R is just going to be 3. So I've got pi times 3 squared, and then for little r, that's the distance between the axis of revolution and the closer part of the boundary of my region here. So I'm going to be doing 3 minus this expressed in terms of y, so 3 minus the f of y function. And we're also squaring that and subtracting all of that here. All right, let me go ahead now and get my limits of integration. So we're going from 0 for the y value up here to 3. So my volume then is going to be the integral from 0 to 3 of this a of y function dy, this thing that I just wrote out here. Now for the calculator. So I'm going to do some work in my y equals. Before I even bother trying to integrate all this, I'm going to put my area function as y2. So I've got pi, I've got my 3 squared minus 3 minus, and this is the f of y function up here. Since I'm doing everything in terms of x, it's going to treat it like I'm doing everything in terms of y when I actually do this integral out on the calculator. So now I've got all of that in there, wrapped up in a neat little box, and I'm going to integrate it. So I've got math 9 going on, 0 to 3. And in here I'm going to do alpha trace y2 and dx, because I've expressed everything in terms of x. Enter. That's about 56.549. On this problem, I want to take the area between square root of e to the y, the y-axis and the x-axis, and this horizontal line at y equals 1, that area, and find the volume when I spin this around the y-axis. So the first part of this that's kind of tricky is this is a no calculator problem. And when you're trying to do one of these problems, visualizing it's half the battle, and that's going to be tough without a calculator on this. So here's how we could do this without a calculator. If you don't know what a function looks like when it's expressed in terms of y, it sometimes helps to express it in terms of x and see if it's a familiar function. So this one, for example, if I want to get the input value to be x and isolate y to get this as a function of x, I can square both sides. So I'll call this x squared equals e to the y. And then if I want to make this y equals something with an x, I need to take the ln of both sides to get y out of the exponent. So on one side, I'm going to just have y. On the other side, I've got ln of x squared, which I can write as 2 ln of x if I pop out that 2. So we know what ln looks like, basically. So just sketching this out, I've got a logarithmic function, and I've got this horizontal line at y equals 1, so it looks something like this. And I need to find the volume when I spin this little area in here around the y-axis. Now that I've got a visual of what's going on, let's see how we could do this. Since my bounded area is flush against the axis of revolution, since the axis is one of its boundaries, that means I can use disks instead of washers for this, so that makes it a little bit easier. So then I end up with a of y equals pi r squared, and for my radius now, that's just the distance from the y-axis to my function here, so that's just radical e to the y that I'm squaring in there. Since I'm doing this by hand, I'm actually going to simplify this to pi e to the y. And now it's time for my integral. So my limits of integration, we're going from 0 to 1 for y values. So integral from 0 to 1, this is going to give us the volume now. And inside here, I'm going to have my a of y function, which, since again I'm doing this by hand, I'll actually write in there. So pi e to the y and then dy. The antiderivative of this is actually not so bad. It's also pi times e to the y. and I'm evaluating that from 0 to 1. So to do this, I'm going to yank out that pi, and inside I've now got e to the 1 minus e to the 0. You could leave it like this, or if you want to simplify it, this is pi times e minus, this is really pi times 1, so minus pi. For this problem, we have this region R in the first quadrant enclosed by these lines in the graph of this parabola, and we want the volume of this thing when we revolve R around the y-axis. So this is a no calculator problem, but we can at least visualize what this looks like. We have a upwards opening parabola above the x-axis. We have a horizontal line through 5, and we have the y-axis itself here. So here's a basic sketch of what's going on. Now we only wanted the first quadrant out of all this, so this is the area right in here, and we're revolving this little area around the y-axis. Okay, so first thing we're going to do, since they gave us a function in terms of x, and we're going around the y-axis, we want to re-express this function in terms of y. So I'm going to start by subtracting 1 from both sides and then square rooting, and I can write x equals square root of y minus 1. So now I can use this to figure out x values, which is exactly what I'm going to need if I'm going to be integrating anything with respect to y. Next, I need an area formula for the cross sections. Since my bounded region here is flush against the axis of revolution, since the axis is one of its boundaries, we're going to be using disks on this one, pancakes. So I'm going to write a of y equals pi r squared, and then r is just going to be the distance from my axis to this function here, which is just the square root of y minus 1. So I'll write pi times radical y minus 1 squared. Now, since I'm doing this by hand, because this is a no calculator problem, I am going to simplify this when I put it in an integral. The only other thing I have to keep track of is what are my limits of integration. So my lower y value in this one is definitely 1, and then for the upper one we've got 5. The volume then is going to be the integral from 1 to 5, and I'm also going to take this pi outside here just so I don't have to mess with it inside the integral. And then inside I'm just going to have the, let's see, square and square root cancel, so this is going to be y minus 1 dy. All right, antiderivative, I'm going to have pi on the outside, and on the inside of my evaluation box, I've got 1/2 y squared minus y. And again, we're going from a 1 to 5 for this one. So I'm going to have pi times all this stuff with 5 plugged in, and we have a big parentheses that we're opening for this, and we're going to be subtracting all this stuff with 1 plugged in. So if this were a free response problem, we could just stop here and call it a day. However, you have answer choices to choose from, so we do need to simplify this as far as it'll go. So for my first brackets here, this is going to be 25 over 2 minus 5. That's essentially 25 over 2 minus 10 over 2. That's going to be 15 over 2 there. For this next one, we've got 1/2 minus 1, which is just negative 1/2. But wait, we have a minus outside, so that's actually plus 1/2 when all the dust settles. 15 halves plus 1/2 is 16 halves, or just simply 8. Pi times 8 is 8 pi. So that's going to be choice B. For this problem, we want the volume of the solid I get when I take the region bounded by these lines and functions over here and revolve it around the y-axis. So taking a look at what I have to work with, we have something defined as x equals f of y, basically. So we're going to have to draw that on our grapher using the draw function, and we have some other lines here as well. Let me just go to my grapher and see what we're dealing with. So I'm going to start by entering y equals 5 in my y equals, and let me zoom 6 that one. There we go. And now I'll graph this other piece by going back to y equals, putting this in there in terms of x, and then using my draw function. So I'm going to y equals again. I'm going to write in here now the square root of x minus 2. And I'm actually going to deselect that because I don't really want to graph that. What I do want to graph, if I quit out of there and do second program to pull up my draw menu, option 8, I want to graph the inverse of that. So I'm going to do alpha trace y2, and now what this is going to do is actually graph out this function right here. So there it is, and we've got this little region in here, and let me just draw it on the paper here, the screen. So this is the region that we're trying to revolve around the y-axis. Now, since the y-axis is one of the bounds of this bounded region, that means that I can just use disks and use pancakes as my cross-section. So I'll be writing out the area formula that we're going to be using in just a moment. But first, let's get the limits of integration while we're at it here. So definitely at the top, we can't go any higher than y equals 5. At the bottom, this looks like 2. If you want to be on the safe side, you could set this radical y minus 2 equal to 0, because that's the x value there. And if you just square both sides and add 2, we get y equals 2. All right. So now we're going to be doing, let's see here, my cross-section area. Again, that's going to be disks. So we're going to do a of y equals pi r squared. The radius in this case is just how far we are from the y-axis, the axis of revolution. And that's given by this radical y minus 2 expression here. So I'll just do pi times root y minus 2 squared. And now that I've got an area formula, let me go ahead and integrate this. For my volume, I'm going to have the integral from 2 to 5. And inside, I'm going to simplify this. Actually, I guess I don't need to simplify this because I'm doing this with a calculator. I'm just going to put in a of y dy here. And I'll do the rest on the calculator. So I'm going to go back to my y equals and do all the heavy lifting there. I'm going to write my area formula in y3. So I've got pi, I've got this basically radical something minus 2 expression squared, and it doesn't matter that it's x's because I'm just going to put dx when I do my integral anyway, and my calculator is going to just pretend I'm dealing with y's. So let me get out of there now, and let me do math 9 for my integral. We're going from 2 to 5, alpha trace y3 for my area function, dx, because I entered it in terms of x in y3, and that gives me about 14.137. So that's going to end up being choice E. On this no calculator problem, they're telling us the region enclosed by x squared and 2x is the base of some solid, and our cross-sections perpendicular to the y-axis are rectangles with a height of 3 times the base. We want an expression that gives us the volume of this solid. All right, so let's start with a visual here. It was a non-grapher question, but we could graph out x squared and 2x pretty quickly to get a picture that looks something like the following. So the big takeaway from here is that we have this bounded region here with 2x on top and x squared on the bottom. Okay, so we need to come up with a few things for this. For one thing, we need our area formula. Since we're dealing with rectangles, let's start with a of y equals base times height. And now it'd be nice if we just had this all expressed in terms of the base, because that's the side that we can actually talk about using y values. So our height, they said, is 3 times the base. So this is really b times 3b, which I can simplify to 3b squared. But I'm not quite done yet. I need to actually express this in terms of y to help me match something that's in the answer choices. So the base is going to be the distance, the horizontal distance, between these two functions here. The trouble is, my functions that I have up here are in terms of x, not y. So I'm getting outputs that are y values, not outputs that are horizontal x values. So I'm going to have to rewrite these. This first one I'm going to rewrite to be, let's see, this is going to be x equals the square root of y. So I'll call that exactly what I just said. And then this next one, we're going to have x equals y over 2. So now if I want the distance between these functions, which is the base of my rectangles, I'm just going to be using, let's see here, this is going to be from right minus left. We've got the square root of y minus y over 2. So we're doing 3 times that stuff squared. Now at this point, just thinking ahead a little bit, to get the volume from integrating all of these rectangles, we're going to take the integral with this inside of it. This is everything that's going inside the integral. The only thing we don't know is the limits of integration. If you look at the answer choices, you already actually have an integral with this exact thing in it. There's only one. It's choice A. And we have this little 3 that we just kind of pulled outside the integral, and that's okay too. So we could actually pick choice A at this point if we were pressed for time. But we also, if we wanted to, could go back and find the limits of integration. So that's just going to be where these two functions intersect in terms of y values. So we can actually take these two rewrites here and set them equal to each other. Radical y equals y over 2. Square both sides. We've got y equals y squared over 4. And then, let's see, I'm going to multiply by 4. That's 4y equals y squared. And then I'll subtract 4y from both sides. Now we can solve by factoring. Just take out a y. So that gives us y values of 0 and 4. So then putting it all together, we have the integral from 0 to 4 of all of this stuff, which I'm just going to call a of y dy, but we know it's all this stuff. So again, that's going to come out to choice A. For this calculator active free response problem, we're told that R is the region in the first quadrant bounded by these two graphs. And for the first part here, we just want to find the area of R. All right, well, to make my life a little bit more straightforward here, I'm going to rename both of these. This first one I'm going to refer to as f of x, and this other one, x over 3, I'm going to call this g of x. And I'm going to graph these out now. So here I am in my y equals. I've entered them both as y1 and y2. And let me just do a zoom 6 to see the basic idea of what's going on here. So we have a square root, and we have this other function, and it looks like we're intersecting somewhere over here, but it's kind of hard to see. So let me restrict my window a little bit. I'm just going to be using, we'll just use 10 as our max, and let me zoom fit this thing, zoom 0, get a better picture. So there's the square root again, there's the line, and let me just draw on here what we're looking at. So this is what's going on. So now in order to get the area of this thing, we can just do top minus bottom from left to right, but we need to know the left and the right. Now on the left, we're clearly intersecting at 0. If you plug 0 in for x for both of these, you get 0 back. So really, it's just this right side that we have to ask about. We could solve this fairly quickly algebraically, but to find where f of x and g of x equal each other over here, I'm just going to go to the calculator. I mean, I've already got this graph pulled up. Let me just do second trace intersect, move my spider over there, 3 quick enters, and boom, we got an intersection of 9. So we intersect at 0 and 9. That means to find the area, I need the integral from 0 to 9 of what? Well, I need to do top minus bottom. The top function is this square root function. The bottom was the line. So I've basically got f of x minus g of x dx inside there. And now I'm going to need the calculator. So I'm going to do a little bit more work in my y equals. I'm going to define a third function, y3, as basically f of x minus g of x right here. And then I'll integrate just that function. So let me do math 9, integral from 0 to 9. And I'm just going to do alpha trace y3 to pull up my area function, dx. And that's coming out to approximately, it's taking a while to think about this, 4.5. It's probably exactly 4.5 if you did this by hand, so we'll just call this 4.5. For this problem, we want to find the volume of the solid generated when this R region is revolved around the vertical line x equals -1. So it's a pretty good idea to actually draw that out or sketch it out, what's happening here, because if you do that, you'll see that we have a space between our bounded region and the axis of revolution. So just thinking ahead a little bit, that means we're going to need washers for this. Before we even think about that, though, let's rewrite these functions as functions of y, because we're going to need that to integrate horizontally here. And then we'll go ahead and see where these things intersect to get our y bounds of integration. So first one, I can write this as x equals y squared, and I'll just call that f of y equals y squared. This next one, I can multiply by 3 to get f of y equals 3y. Now, where do these things equal each other? We're going to intersect at 0, the origin, but also up here, if we just go back to the calculator, so we can grab that other intersection value, let me do second trace intersect again. Whoops, that's another function that I don't need. There we go. Second trace intersect, now that we don't have any unwanted graphs on here. Enter, enter, enter again, because I wasn't paying attention the first time, and I see the y value there, which is what we're interested in now. The y value is 3. So these things intersect at 0 and 3. Those will be our limits of integration. Now we need an area function to integrate. Now again, we have this space here, so we're going to use washers. A of y equals pi times big R squared minus little r squared. For big R, that's the distance from my axis of revolution to the further away of the bounding functions. So this function here, this was 3y. So the distance here, the positive distance, we're going to write as 3y minus negative 1, or 3y plus 1, I guess you could call it. Or you could call this g of y plus 1. That also works. And we're squaring that. Now we're going to subtract the square of, this is going to be f of y plus 1. And we're going to need the calculator for this, but the general setup, we're going to have the integral from 0 to 3 of a of y. And I'm calling this a sub 1 of y, I just noticed. I'm doing this because there's another area function I'm going to be writing on the next part of this problem. So I don't want to mix it up with this one. So we have a sub 1 of x, or y rather, dy. Now it's time for the calculator. So I'm going to put my whole area function here inside my y equals under y4. So I have the pi outside. Inside I have g of y, which is 3y plus 1 squared, minus, and this is now going to be f of y, y squared plus 1, and we've got that whole thing squared. Now I'm doing all of this stuff with x's instead of y's because my calculator recognizes x as the input variable. But as long as you're consistent and use x's everywhere, you can basically do this on your calculator without putting y in there. So let me quit out of there now, and let me do an integral. Let me clear out everything else. We're going to do an integral from 0. Let's try this again. Math 9. Integral from 0 to 3. And now I'm just going to do alpha trace y4, because that's where I just stuck this latest area formula, dx. And all that's coming out to about 130.062. For this last part of the problem, they're telling us our region here is the base of a solid, and we have cross-sections perpendicular to the y-axis, so going like this, that are going to be squares. We want the volume of this. So let's start by getting the area of the cross-section, the squares. I'm going to write in general a of y equals s squared, and I know it's a of y because they said this was perpendicular to the y-axis, and I'm going to write this as a2, a sub 2 of y, because I already used a different area formula in part B that I don't want to mix up with this one. All right, so we have to define this actually in terms of y. So recall from part B, and here's part B again, we rewrote these two functions in terms of y. So we had f of y equals y squared, that was this function here on the left, and g of y equals 3y, that was our function on the right. So then coming back to the current problem, the base of these squares is just going to be the distance between those two functions there. So we can write this as g of y, the rightmost function, minus f of y, the leftmost function, and that whole thing squared. That's going to give us those square areas. Next up, we need an integral. We're again going from 0 to 3. So I have the integral from 0 to 3 for volume, and it's just of this a sub 2y dy function, which I will now do on the calculator. So on the calculator, in my y equals under y5, because I already used everything before that, I'm going to put x squared minus 3x squared. That's this area function. So this x squared, this is really the y squared that g of y is. And then 3x, that represents the 3y for f of y. Squaring all that. Let's quit out of there now. And I'm going to grab my input from before. This was for my area function from part B, but everything else is the same, so I'm just going to go in here and replace y4 with, let's see, alpha trace y5 is what I want now. Press enter, and that's exactly 8.1.